Hi there. Thank you for joining us. This is Space Nuts, and it's a Q&A edition. My name is Andrew Dunkley. What's Q&A stand for? I don't know. But we've got questions from our audience, which we will answer. Oh, there it is. Casey wants to know about dark matter stars, even though they don't exist and we can't answer the question. Michael, he's sent one in about dormant comets, which I found most intriguing. So it'd be interesting to discover what that's about. Derek is asking about gravitational slingshots. And Jason is asking what Fred thinks of the new wave of smart telescopes. Ooh! We'll talk about all of that on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And he's back again to try and sort all that out. It's Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Very good to see you again.
And you too. It's been minutes.
It has. I might add a postscript to when we recorded the last session.
Yeah.
I just got back from the annual science meeting of the Astronomical Society of Australia, and I meant to mention that an old friend of Space Nuts was there, and I had dinner with him on the first night, and that is Peter Verweyen, who is our contact in the world of modified Newtonian dynamics.
Yeah.
So.
Terrific.
Nice to do. He's still monding, although I think he's had some hurdles to overcome. So we might have to do an update on that down the track.
Well, while we're sending shout outs, I'll send a shout out to an Instagram person named the Greens Goddess. A female golfer who started following me, I don't know, some time ago, and I thought I'll do the honour of following her back. And she posted a video of her swing the other day, and I noted a couple of issues with it. So I sent her a note and said, look, you got a bit of a reverse pivot going there. Try this drill to sort it out. Anyway, she sent a note back and said, oh, that's very helpful. By the way, big fan of Space Nuts.
Okay. That's nice.
Which might have been why she followed me in the first place, but anyway.
Good on the Green Goddess. I like that.
Good for her. All right. Shall we answer some questions, Fred?
Yes, we might as well, might we? Now we're here.
Let's get into our first one, and it comes from one of our regular contributors. This is Casey.
Hello, Fred, Andrew, and Hugh. This is Casey from Colorado. I know that dark matter stars are completely hypothetical at this point. I've read before that they would be some of the brightest objects in the sky if they do exist, though. I was wondering if you could please explain why that is, and also how they can get so hot without any fusion. Hope you're both well, and thanks for the podcast.
Thank you, Casey. I just knocked everything over on my desk, but it'll wash out. Dark matter stars. I think somebody's brought these up once before, if I'm correct in my thinking. But maybe we should start by trying to explain what they're supposed to be.
Yes, well, that's right. It's First of all, dark matter is still hypothesized, really, notwithstanding what we're just saying about Peter Verweyen. That is an alternative theory to try and account for the way the galaxies tell us that there is something there that we can't see. His version of that is something called modified Newtonian dynamics, that suggests that accelerations do not follow the normal Newtonian rules at very low levels. I think that's going into doubt though now. So I suspect that dark matter is basically consolidating its position as the number one theory for why galaxies don't just fly apart, because they've got all this stuff in them that we call dark matter. So I think it's true to say that despite a few people looking in other directions, most of the scientific community believes that we are in a universe whose matter content is dominated by something that we can't see. It sort of outweighs normal matter by 5 to 1.
Yeah.
And it's probably some sort of subatomic particle that we just have not come to grips with yet. Now, once you accept the idea of new species of subatomic particles that only interact with everything else through gravity, they don't interact through electromagnetic radiation or any other kind of particle physics. It's only gravity that lets us know that these things, these dark matter particles are there, hypothesized still, but likely to be there. And it's their own gravitational attraction that stops galaxies falling apart or flying apart because they're rotating too quickly. So that's what dark matter is. Now, on that bare framework or foundation, scientists have built up some models of what dark matter particles might be. And in particular, there is an idea that if dark matter particles come together, then a bit like matter and antimatter, they would annihilate and basically produce radiation. And that's the idea of a dark matter star, that you've got a hypothetical object bigger than your average solar system. So they're very large.
Wow.
Made of dark matter. But what makes them shine is the dark matter particles self-annihilating. And there are some pundits who believe that the very first stars that formed when the universe was in its infancy were actually dark matter stars. Were these ones that are super bright in the sense that they emit a large amount of radiation, but not super bright in a way that you might imagine. And that's because they are so big, they are basically puffed up by the energy coming from this radiation. But because they're so big, their surfaces are relatively cool. And so what you see is an object in the infrared, if you're looking out for a dark matter star, or what you would see if they existed.
Yeah, I get it.
So that's basically where the energy comes from, the annihilation of dark matter particles, self-annihilation. But they're bright because of the amount of radiation that they generate with these annihilation. That makes them bright, and they get to something like 10 billion times more energetic than the sun in terms of the energy that they release. But as I said, it's infrared radiation, so they're really releasing it in the form of heat.
So in terms of naked eye observation, you can't see a thing.
I think that's right, yes. I mean, they would also be, if we're seeing them in the early universe, these things will be very highly redshifted. That means their light will not only be infrared, but it'll be even redder than red infrared because of the expansion of the universe stretching out the light waves. So they might be quite difficult to detect. However, it's basically one of the things that the James Webb Telescope is looking for. It's looking for any evidence of dark matter stars.
So where a normal star like ours depletes its fuel and then turns into a red giant and then collapses into a white dwarf, a dark matter star annihilates itself.
I think that would be right. I think it would just basically fizzle out. Evaporate and fizzle out, yeah.
Okay, wow.
Yeah.
Thank you, Casey. Haven't found one yet, but if you do and to stumble across one, let us know.
Just hand it in, please.
Yes. Just don't forget to put it in a lead box.
That's right.
Yeah. Thanks for the question. Our next question, Fred, comes from Michael. He said, I understand that, he says, Andrew, I apologise. I still do not have questions about dark matter. It's all right, person before you did it, as I have a firm understanding of how coffee and Coca-Cola power my day. I understand that dormant comets have been suggested, with a few even confirmed inside the snow line. I'm wondering how many might exist. 7. There's 7. I have no idea. And how a best guess might be made to arrive at that number. It was my best guess. I'm going well here.
You're guessing well.
Other than infrared telescopes and cameras looking for low-temperature dark objects, what instruments on a smaller satellite might be best for searching for either or both of the Earth-Sun Trojan Lagrange points? That comes from Michael. Now, I'm assuming Michael's in Alberta because I'm going off his email address, and it had the abbreviation AB, and I looked that up, and that's the abbreviation for the province of Alberta, Canada. But I might be wrong, and I'm sorry if I'm way off the map, Michael, but thanks for the question. Okay. Are there
yes, there are
dormant comets?
Thought to be. So what's a dormant comet? Well, it would be a comet that has gone past the sun several times in its lifetime. I think that's probably the bottom line. It's an old comet, and because every time a comet gets near the sun, it basically radiates its gas and dust into space. The gas turns into a kind of plasma. It's excited by the sun's radiation, and so you get what we call a gas tail for a comet. And you can also get a dust tail because comets are dusty objects with this sort of frozen gas around them. The dust leaks out when the gas blows away, and so you get comets that have two tails. So imagine one of these things that's gone around the sun several times, and basically it would have a kind of crusty layer to it, an outer layer, which is the dust sort of coagulating on the surface. So the gas has been blowing dust off, but there's still a residual dust layer that might give you this crust around the edge of it. That means that even though it goes near the sun doesn't penetrate, the sun's radiation and heat don't penetrate the dust, and so it doesn't actually stir into action. It doesn't start behaving like a comet, which is to release its gas and dust.
Okay.
And so that would be a dormant comet, one that's gone to sleep. What might stir it back into action is if you had a dormant comet colliding with something else, hopefully not the Earth, but maybe an asteroid or something like that, that might disturb that dusty crust on the outside, or crusty dust, the sort of crust over the ice. And then if you could expose the icy surface to the sun's radiation, then it would basically start giving you what we would call an active comet as well. I mean, the way they are, and this is really the nub of the question, I guess, how do you detect them? Because the problem is, if you've got a comet, even though it's made mostly of ice, if it's got this dark crust on the outside of it, there's very little to distinguish that from an asteroid. And so how do you know whether this is a dormant comet or an asteroid? And it's really quite hard to do. There's not that much to choose between them. You will be looking at a kind of thermal signature because asteroids are cold rock. Dormant comets are cold ice with a kind of rocky sort of dusty rocky layer on the outside. There's not that much to differentiate between them until you knock some of the dust off and the thing wakes up.
Yes.
Yeah. So I think I think there's scope for us trying to do a survey, but it will be hard to know whether you've picked a dormant comet or you've got an asteroid. And it may well be that some of the asteroids that we consider to be asteroids are actually dormant comets.
So they're super duper old. I suppose the smoking gun would be most of them have got Zimmer frames.
Could be, yep. Comet Zimmer frame. Yes, I'd like the sound of that.
You never know. Worth looking for. or not. But yeah, okay. So they might be out there. When Michael said that a few have been confirmed in the snow line, what's he meaning there?
So that means the snow line is basically it's on the far side of Mars's orbit.
Yeah,
it's where water vapor stops being vapor and freezes.
Okay.
It's the sort of outer side of the Goldilocks zone.
Okay, fair enough. Michael, thanks for the question. That was fascinating. And I suppose one day someone might go, aha, I've found a way. And then we've got the answer. This is Space Nuts. Andrew Dunkley with Professor Fred Watson.
Space Nuts.
Oh, that was it. That was so short, I'm going to do it again.
Space Nuts.
Yeah, he's got a very nice voice, hasn't he?
He has, yes.
Yeah.
I can do that on my machine. Hang on. Yeah, wait for it. Not there. Okay, no, not there. Oh, here it is.
Space Nuts.
That's all right. Yeah, I think you need some Gaviscon or something for your digestion.
I can do it with this one.
Space Nuts.
Yeah, I could go on forever.
I know you could,
but I won't. We'll go to our.
Anyway, I'm sure you can use that in suitable environments audio environments that might intrigue our listeners or otherwise confuse them.
Indeed. Our next question comes from Derek.
Hi, guys. This is Derek from Southern Ontario in Canada again. Just wondering if you could explain the orbital mechanics behind slingshots, gravitational slingshots. And I'm trying to understand whether the rotation of the planet has anything to do with that slingshot, or if it's just in terms of how close you get to the planet. If you can elaborate a little bit on that, that would be great. Thank you. Love the podcast. Have a great day.
Thank you, Derek. It's a good question, and I think we've seen it used many times for some of these probes that have been sent way out into the solar system, because we find it's a much more efficient way of doing things, because we haven't got the fuel to send them all the way in under their own steam. That was certainly the case with the Voyagers. And they were two of the best examples of using the gas giants for slingshots. But even launching things off our own planet, there's a bit of slingshot effect, isn't there?
Yes, that's right. There is. It's not just getting to the outer solar system. I think the Bepi-Colombo spacecraft, which is on its way to Mercury, I think that's had something like 7 slingshots with Venus and the Earth. And
that's right.
I might be exaggerating, but it's had a large number, and that's in order to make its velocity match the velocity of Mercury, which you'd think would be easy as you drop things into the inner solar system, but it's not actually. It's quite hard to do. You've got to kind of catch up with Mercury as it steams around in its orbit, because it's going faster than the Earth is in its orbit around the Sun. So it's a very useful tool for exploring the solar system. I think you're about to confirm how many it's had, are you?
I haven't found it yet.
Oh,
I'm usually pretty quick, but I'm not.
You are pretty quick, yeah.
It's proving elusive at the moment, but I'll get it. I will get it.
It has had an elusive number of slingshots, but the bottom line is that it's a process that works well and is actually very much a part of the astrodynamicists' toolkit when they're actually working out the orbits and trajectories of planets, exploring the spacecraft.
Nine slingshots.
9 slingshots. There you go. 7 was an underestimate.
Yeah, one at Earth, 2 at Venus, and 6 at Mercury itself.
Yes, fantastic. That's what you need to match Mercury's orbital speed. Quite remarkable.
Yeah.
So, how does it work? Well, it's counterintuitive, isn't it? Because you think that a spacecraft falling in towards a planet, it's going to gain velocity, but then as it leaves the planet, it's going to decelerate, and so it would lose velocity. And you might think the two would balance up. But the bottom line is they don't. And it's all about the angle that you come in when you intercept the planet's orbit. And if you get the angle right, you can have this situation where, without making contact at all, where some of the momentum of the planet is transferred to the spacecraft. And so the spacecraft gets a push in velocity. Its velocity increases. The planet doesn't even notice the difference because the spacecraft has so little mass compared with the planet. So it's balancing the velocity, the momentum. Momentum, of course, is just the mass times the velocity. And so you've got a very big mass transferring momentum to a very small mass, and that means you get quite a significant velocity kick in doing that. And so it's not to do with the rotation. So Derek is right to point out that as a query. Is it to do with the rotation? The answer is no. So if you had a planet that wasn't rotating at all, you could still do a gravitational slingshot very successfully with it.
Oh, okay. Okay, so does the spacecraft, when it's doing this slingshot, actually steal some of the planet's energy?
Yeah, that's
Is that how it
exactly
works?
it. It's stealing momentum, and using that to accelerate, and sometimes quite dramatically so. The change in the orbital trajectory is really significant. But it's a fantastic tool for exploring the planets.
Yeah, it is, until the day we can come up with a new way of a new form of engine. Propulsion, that's the word I was wanting, that renders gravitational assist unnecessary.
Yes, that's right. At the moment, we haven't got there yet.
No.
You're right. Yeah.
But it might, it could be scramjet technology, it could be nuclear power, like fusion engines, things like that. We're a long way from that, but those are possibilities.
Yeah.
Yeah. Who knows? But the more you speed up in space, the more you've got to be careful, because there's lots of stuff you can bump into. You don't really want to do that at pace, do you?
You've got to know where all this stuff is, and that's what astronomers are for.
Indeed.
To tell you where it all is. Yeah.
Thank you, Derek. I hope that covered your question adequately.
0G, and I feel fine.
Space nuts.
What we're going to do now, Fred, is we've had quite a Canadian influence in today's show by the look of it. This comes from Jason in Montreal in Quebec, and he says, I'm a big fan of the show. I have a question regarding the rapid rise of fully automated smart telescopes and their place in the modern hobby. On one hand, it feels like these devices are an incredible, cost-effective gateway. They allow beginners to dive straight into astrophotography and see almost instant results without spending thousands of dollars on complex gear right away. That immediate reward seems to be a fantastic way to spark a lifelong interest in astronomy. On the other hand, there seems to be a bit of a divide in the community, with some traditional astrophotographers viewing them as cheating because the automated software removes so much of the steep learning curve. What are your thoughts on this technological shift? Do you see smart telescopes as a positive tool for opening up the night sky to a broader audience, or do you feel something valuable is lost when we automate the setup and tracking process? I actually bought one recently, and I've already learned a lot over the past few months. Getting those quick results didn't stop me from wanting to learn more. In fact, it did the opposite. It got me watching more astronomy and astrophotography videos than usual on YouTube, and joining Facebook groups to learn from other users. And of course, let me find your podcast. Thank you for the great episodes. That comes from Jason in Montreal. I'm going to show you something, Fred.
Yep. Let me see. I've
got one.
He's got one.
I've got one. And yes, it simplifies everything. It does all the hard work for you. But if you're someone who doesn't like doing the hard work, it's a godsend.
Yeah.
But that's my take on it. I'll keep it nice and short. I know a couple of people who've got both. They've got a traditional telescope with the whole kits set up with their computers and the programs and all the tracking technology. They like to do it the old-fashioned way, and they've also got smart telescopes, which do the same thing. But you've got to rob Peter to pay Paul. The efficiency and simplicity of that also means that your images aren't going to be nearly as good as a traditional telescope. So it ebbs and flows. There's a cost for the let's not say the word cheating, but there is a cost. But it does make astrophotography immensely affordable for a lot of people.
Yeah, and accessible too.
Yes.
So yes, look, I think I think Jason sort of answered his own question in exactly the way I would. That you've got the two aspects of it. It's a brilliant way of getting into astrophotography almost painlessly, and on a very good level too. And if you then wanted to do more, if you wanted to go for a bigger telescope and do your image processing in a more perhaps a more precise way, that's still open to you. I think as a tool for getting people involved in astronomy, I think they're absolutely fabulous. I don't have one myself. I'm glad you've got one, Andrew, because I've seen some of the results from that, and they are very impressive. I've got a number of other friends who've got them as well, who are themselves professional astronomers. So
there's a photo I took the other night of the M8.
Yeah, there you go. And it's lovely colour balance. That's pretty well what you'd expect to see from a David Malin image.
Yeah, and that's what's like David Malin was a pioneer in this stuff.
He did.
Now you can do it from your lounge room.
Yes, you can, literally.
With your mobile phone.
On your mobile phone,
that's
right.
It's amazing.
Smart telescope outside. I think it's fantastic. I'm very much old school. I love pottering around with a telescope with nothing more than an eyepiece. I've never really ventured into astrophotography. The nearest thing I've got to that has been a lot of aurora photography, which I love, and is now also a lot more accessible just with a smartphone. So I don't carry around all the kit I used to when we go up to the Arctic to look for the aurorae. I just take my smartphone.
Yeah.
But you're right. I think, as I said, I think Jason's answered it perfectly. It's obviously stimulated him to go further. He loves what he's got, and he's finding out more. Best of all, he found space nuts. That's nice. But it's I would not be somebody who would frown upon these devices and saying, in my day, we did not have this sort of thing, we had to do it properly. We had to understand what was going on. Well, you can still do it and understand what's going on with your smart telescope.
Well,
sorry, go ahead. Andrew.
Mine, when I pick a target, it then gives me an audio briefing on what the target is, who found it, when it was found.
See, that is fabulous.
It's amazing.
Fantastic.
Yes, it's good stuff.
It's an astronomy class as well. I think I'm right in saying that the first of these smart telescopes was the Unihedron, I think. That was probably 6 or 7 years ago when I saw the first one of those, and I was very impressed with it. But what I was going to say was that they have now come down in price to be really quite affordable.
Yeah.
And it's not beyond the realms of possibility that one day there might be one in the Watson household. Although I do like things that are made of brass, and you look through one end and see out the other.
There are a mass of them out there, and quite a few are well under $1,000.
Yes.
So, that makes that makes a pretty wide target audience. The other thing mine does is you can click on the map on your phone, and you can see where other people are that are using the same gear as you.
Interesting.
So I'm not sure that goes down with the privacy laws, but anyway.
I was going to say, is there a privacy infringement there? Maybe not.
I've got satellite navigation in the car that does the same thing. It shows you other users of that particular device, but they've curtailed it in Australia, so it only shows you where they were like 10 minutes ago. So,
okay,
which is pointless. Just turn it off.
Yes, it is a bit of a waste.
Yeah. But, well, we live in nanny state New South Wales, so you've everything's on the table for some sort of scrutiny. Probably me now after saying that.
Yeah.
But Jason, look, I'm a big fan, and you are too. And I don't think it does spoil the tradition or the traditional approach to astrophotography, because vinyl records have come back. So
Yes.
You can't write anything off. Yeah.
No,
But I wanted
right.
that question to. I wanted you to hear that question, Fred, because I know you've got a long history in telescopes. You've written books about them, and this is the next big thing, I suppose. While we're talking about it, when you were away last, Jonty Horner grabbed a couple of astrophotographers, and we did a special on astrophotography, which I'm not sure if Hugh's released it yet, but I think he's still working on how to get that out there. It's I think it's an hour-long special on astrophotography and the techniques and how they did it and what you can do. So if you really want to get into the nuts and bolts of astrophotography, have a look for that one. I'm not sure it's been released yet. It took some pretty heavy editing because there were 4 people on it, so it was a big show. But that one will be available soon, if not already. And thanks for all your questions. Please keep them coming at our website, spacenutspodcast.com or spacenuts.io, and click on the little AMA tab at the top and send us your text or audio questions. If you're sending us an audio question, please remember to tell us where you're from and your name. It doesn't do that by itself, although I know sometimes people forget to tell us their name on where they're from on text as well. But that's okay. It doesn't, it's not mandatory, but it just helps us to know where everybody's at. Fred, we're done. Thanks very much.
Oh, thank you, Andrew. Good fun and great to hear from the listeners as well, especially, when we get questions that cover everything from dark matter stars and dormant comets to the latest in telescope technology.
Yes,
where else can you hear about all that?
Exactly right. Yeah. All right. Thanks, Fred. See you soon.
Yeah, cheers. Cheers for now.
Professor Fred Watson, astronomer at large. And thanks to Hugh in the studio. Couldn't be with us today because he bought a smart telescope. He's not smart enough to use it. And from me, Andrew Dunkley, thanks for your company. We'll catch you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.